see that the one up here takes it out to, well, you can't see. But what was the first one? Aluminum. Here they got 26.9815386. All right, so they're taking it out to 2, 4, 6, 7 decimal places. 9 significant figures. That's more accurate number than our number there, but for all of our intents and purposes, these numbers are plenty accurate. Okay, well, let's get it under our belts here, how we can go from moles, 3.97 moles of aluminum oxide, and we're going to convert that into grams of aluminum oxide. All right, so, and we're going to use the molar mass. And the molar mass is 101, let's use that number, 101.96 grams per mole. So the mole is going to go down here, because that's what we want to cross out. And it's 101.96 grams of aluminum oxide per mole of aluminum oxide. And we convert the moles into grams. And what do you get for that number? Now notice here we've got 3 significant figures. So you can round your answer off to 3 significant figures.
405.
What?
405.
That good? Agreed? All right, these are essential skills. Determining the molar mass of any compound or element. If we were working just with carbon, the molar mass you can get right off of the periodic table. You don't have to do anything, just read it right there. 1 mole of carbon is 12.01 grams. 2 moles of aluminum is 2 times that number, and 3 moles of aluminum is 3 times that number, and 1 mole of this has 2 aluminums and 3 oxygens in it. All right, now going, so here was, this is a moles to grams. This is an essential skill. Here is grams going to moles. So here we were beginning with 545 grams of aluminum oxide. And what do we want to know? How many moles? Okay, so I'll just leave that on the board, and then I'm going to be writing down 3 or 4 other problems here in a minute. But let's introduce the chemical equation. Now I like to do this. I like to kind of get your feet on the ground. Imagine you're heading to Pittsburgh. I got 2 of my grandkids flew in from Pittsburgh last Friday. I was born in Pittsburgh, by the way. That won't be on the test. All right? But I was born in Pittsburgh. It used to be Pittsburgh Steelers used to be the capital, the steel capital of the world, but it is also the headquarters of Alcoa, Aluminum Company of America, the Aluminum Company of America. So just imagine that you're getting ready for an interview at Alcoa, so you want to know a little bit about their industry. And I'm going to use Alcoa as an example to introduce the chemical equation. So what does Alcoa do? They make aluminum. They make tons and tons of aluminum. That frame around that bulletin board is aluminum. This is aluminum. Airplanes have a lot of aluminum in them. Electrical wire, aluminum cans. Let's see, anybody got a soft drink? Aluminum cans, so we use it to package things. So there's aluminum in so many different industries. And what they do is they take aluminum oxide. Well, I'm not sure this is their reaction, but you can take an aluminum oxide and carbon and react it with a lot of energy and produce aluminum and carbon dioxide. All right, there it is in words. What do chemists do? They distill this down into formulas and write a chemical equation that describes that reaction. And you know that aluminum has a +3 charge, oxygen has a -2 charge, so you end up with that formula for aluminum oxide. It's reacting with an element, carbon. So we just write the chemical symbol for that element. The arrow, what we have here is the reactants, an arrow leading to the products. All right? The aluminum is Alcoa's product. That's what they sell. Sell it by the ton. So they get aluminum, they get elemental aluminum, and carbon dioxide. What is carbon dioxide? CO2. And there's the essential start of a chemical equation. And what have we done? We have written all of the reactants and the products with their correct formulas. We've got the reactants on the left, the products on the right. Okay, now, before we get into balancing this equation, how do we balance this equation? Let me just introduce you to some subscripts or some qualifiers that you see at the end of this. Sometimes you'll see this. You'll see an S there, an S there, an S there, and a G there. Now the G is not grams. These things here in these parentheses are indicating what is the physical state of that material at room temperature, 25 degrees centigrade. What physical state is it in? Is it a solid, a liquid, or a gas? And aluminum oxide is a solid. That's bauxite. That's what they mine. So at a mine, they're digging the bauxite out of the ground as aluminum oxide, and they want to get it down to pure elemental aluminum. So that's a solid at room temperature. Carbon is a solid at room temperature, like what's in a pencil. Aluminum is a solid at room temperature. Carbon dioxide is a gas. Some of the other things you'll see. So you'll see a solid. You'll see liquid. So you might see this. And so if water was a reactant or a product of a reaction, it would be with an L after it. Gas. Sometimes you'll see this, AQ. AQ, what does that mean? Aqueous. It means that material is dissolved in water. So let me give you an example of that. You could have sodium chloride. If you saw sodium chloride like that, it would be referring to what's going into this or coming out of this reaction is white crystal sodium chloride. Sodium chloride crystals. But if you saw this in an equation, it would say that the sodium chloride is dissolved in water. You have a solution of sodium chloride. This is how you're introducing it. Excuse me. How you're introducing it into the reaction or how it's coming out of the reaction. All right, so just be aware of that. I'm going to erase all that. And now get back to balancing this equation. All right. Balancing the equation. Number one, okay, what do we mean by balancing the equation? We want the same number of aluminums represented on aluminums, carbons, and oxygens represented on both sides of this equation. The law of conservation of mass basically says that a chemical reaction will not create nor will it destroy matter. Every gram of reactant that goes into a reaction will come out of it. It may be in a new form, may not be the same form it was in originally. Here we've got aluminum, we're going to get aluminum. But we should have the same number of aluminums, carbons, and oxygens on both sides of this equation. Do we have that? No, we don't. It's out of balance. That equation is not balanced. We'll balance it in here in a minute. But let me point out one other thing. One thing you will never see is an element over here that you don't see over here. All right? Every element that you see in the reactants has to come out of that reaction. So if you ever see a reaction written out and you see Al2O3 plus carbon yields aluminum, iron, and carbon dioxide, it's wrong. You can't produce iron from aluminum oxide. Can't do it. All right? You can do it with a nuclear reaction. Nuclear reactions can convert an element to another element. Chemical reactions never do that. They never convert one element to another element. All right, so balancing equations is I can't just kind of give you three easy rules for here's how to balance a chemical equation. Best I can tell you is practice balancing chemical equations, and you'll start getting a feel for it. All right? So, I mean, you look at this and you see you got two aluminums, you've got one carbon, and you have three oxygens. How am I getting that? Well, Al2, that 2 refers to that. There's two aluminums represented here. There is only one carbon, and there are three oxygens. And on this side of the equation, I got one aluminum, I have one carbon, and I have two oxygens. CO2. With me? John, you with me? All right? I've got two oxygens. It's out of balance. Well, I mean, you can look at that and you say, well, okay, that's in balance. That isn't out of balance. That isn't in balance. The only way I can balance this is with coefficients. Okay, here's another good solid rule. Never change a formula. Don't change a formula to get it balanced. I mean, I could say, well, man, if this was just CO3, wouldn't that make my life a lot easier? But CO3 is not carbon dioxide. It's carbon trioxide, which isn't really even a compound. So you can't fiddle with the formulas. You need to get the formulas right to begin with before you start balancing the equation. Now, from experience, I can look at that and say the best place to start here is on the oxygen. Look, the aluminum looks easier. I can just put a 2 in front of the aluminum here, and I've got it balanced. So that looks easy, but that still leaves my oxygen. I still got to attack the oxygen somehow. So start with the oxygen. And what is a number of oxygens that you could get on both sides of that equation? 6. 2 times 3 is 6. So if I put a 2 here, what I'm basically saying by putting that coefficient there is that I have 2 of these. Okay? Students quite often, they'll put a 2 right there and they'll think, oh, that's 4 oxygens, but they'll not realize that that's 4 aluminums, but that's 6 oxygens. 2 times 3. There's our 6 oxygens. So that gets me to 6 oxygens, gets me to 4 aluminums. All right? 2 Al2O3s, there's 2 aluminums, and 2 aluminums, 4 aluminums. All right, so now how do I get 6 oxygens on the other side? What do I put in front of the CO2? 3. So that gets me 3 carbons, because what that is this. That coefficient, saying now I'm producing 3 carbon dioxides. So that's 3 carbons, and that's 2, 4, 6 oxygens. All right, so now come back and fix the carbon. 3 right there. Come back and fix the aluminum. 4 right there. And it's balanced. All right? Yeah, don't start with the carbon and aluminum. They're just sitting there all by themselves. So when you get the other things organized, the oxygen, you can come back and settle the carbon and the aluminum pretty easily. Putting a coefficient in front of there doesn't affect any other element. So now it's balanced. So we have 2 aluminums, we have 3 carbons, yielding 4 aluminums and 3 CO2s. That's what those coefficients are telling you. That's what it really is. All right. Now we could read that the 2 formula units of aluminum oxide yield plus 3 carbon atoms yields 4 aluminum atoms plus 3 CO2 molecules. That's it at the atomic level. But if we multiply those by Avogadro's number, we would convert and multiplied every one of those coefficients by Avogadro's number, which is 1 mole. We would convert that into the moles of those things. So the way we really do read this and use it is this. We say that 2 moles of aluminum oxide reacts with 3 moles of carbon to produce 4 moles of aluminum and 3 moles of carbon dioxide. Jose?
How do we know what, I know you talk about those like subscripts, like solid, gas, and liquid. How do we know what's what if we're looking for?
Well, how would you know?
So like aluminum and oxygen, how would you know it makes a solid?
How would you know that? How would you know aluminum oxide is a solid? Good question. Yeah, some things you will just know from experience. Okay, if I talked about carbon dioxide and say, what is that? You say, well, that's a gas at room temperature. What about nitrogen? That's a gas. Oxygen's a gas. So some things you'll know from experience. Most things are solids. One thing that can help you, Jose, is this periodic table. All of these things are solids. That's a liquid, and that's a liquid. This is color-coded. This one is. These are the only 2 elements that are liquids at room temperature. These are all gases. The red ones are all gases at room temperature. And any one of these combining with anything is going to be a solid at room temperature. Lead oxide, lead sulfide, iron oxide, aluminum oxide, aluminum sulfide, potassium oxide, those are all solids. So 90, don't worry about these. This is probably the least, I'll show you one type of chemical reaction where you're going to look at those subscripts as a hint for what's going on. But for the most part, that's not our major concern. You could look it up in a table. You could look up a table of compounds, and it would tell you its melting point, and you'd know whether it's a solid, liquid, or gas at room temperature. Okay, now let's look at 4 types of problems. I think I'll put these on the board. I'll also try to capture them on here. This is the simplest, converting moles to moles. I wish I had a way of, there probably is a way for me to make copies of this right here so I could just keep doing these problems right underneath it. I don't know if there's a way for me to copy this, but at any rate, moles to moles. This would be the simplest one, like let's give an example. How many moles of aluminum can be produced from 35.3 moles of aluminum oxide? Well, 35.3 moles of aluminum oxide. Okay, what we have in this balanced chemical equation is that you get 4 moles of aluminum for every 2 moles of aluminum oxide. That's what those coefficients are telling you. You get 4 moles of aluminum for every 2 moles of aluminum oxide. This is a child-proof container, which means only children can get it open. dead battery. Okay, so we get 4 moles of aluminum for every 2 moles of aluminum oxide. These coefficients are now telling you the molar ratios of anything and everything in this chemical reaction. So if I have 35.3 moles of aluminum oxide, and I want to convert that into moles of aluminum, I can use this relationship right here. 4 moles of aluminum. Now I got to put the moles of aluminum in the numerator and the moles of aluminum oxide in the denominator, because I want to convert into moles of aluminum. And these coefficients tell me that relationship. So we're going to get 4 moles of aluminum for every 2 moles of aluminum oxide. You multiply that out. You can divide both of those numbers by 2. And we can almost do this in our heads. 2 times 35 is 70. 2 times 3 is 6. 70.6 moles of aluminum. Okay, I'm gonna call this problem number 4. All right, we got our 3 key skills over here. Here's our 4th one. Using a balanced chemical equation to show the molar relationship between, and to convert from moles of one compound in the reaction to moles of another one. Yes?
Do you have to account that aluminum is diatomic on this one to produce aluminum by itself?
Say that again.
Like, in the equation, aluminum is diatomic. So
Well,
it's-
okay, I wouldn't call that diatomic. It's Al2O3. That's a compound. Nitrogen is diatomic. It's a molecule of 2 nitrogens. Okay? So yeah, you don't have to worry about that. No, don't worry about that. You've got these coefficients, so you don't need to compensate for anything regarding the formula. We did that in balancing the equation. We took that into consideration when we balanced the equation. So no, it's just straight off of that. I could have come up with, I could have asked any question here. I could have said, how many moles of carbon dioxide would be produced if 35.3 moles of aluminum was produced? You could relate any 2 things. It doesn't have to be a reactant to a product. It could be, if I'm going to get 12 moles of this, how many moles of carbon dioxide would I get? If I produce 12 moles of aluminum, well, you're going to get 3 moles of CO2 for every 4 moles of aluminum. So you could ask this kind of question about any 2 things in that equation. Number 5. Let's say how many grams of CO2 will result from the complete reaction of 12 moles aluminum oxide. Okay, now here we're going from moles of something to grams of something else. Grams of something else. So we're starting to get from moles to grams, mass relationships. Now let me lay out the strategy for this. This is number 5. We're going to go from moles of aluminum oxide. We're going to convert to moles of CO2. and then we're going to convert that into grams of CO2. Why are we going to go through this step? We're going to go through this step because that's what we know. We know the relationship between moles of aluminum and moles of CO2 from this equation. That is not a direct moles to gram relationship, but we can figure out the grams. Okay, let's see what that looks like. So this was number 4. Here's number 5. So we want to, how many grams of CO2 will result from the complete reaction of 12 moles of Al2O3? So we got 12 moles of Al2O3, and we want to know grams of CO2. See, here's how I do problems. This is what I'm given. I know this. This is what I want to know. This is where I'm headed. All right? You jump in the car. You don't just jump in the car and start driving. You usually know where you're going, don't you? And you pick the roads that you want to do to get there. You have a strategy. You have a path you want to go on to get there. So we're going to have that here. So now I'm going to put moles of aluminum oxide down here. And I'm going to put moles of CO2 up here because I want to convert from moles of this to moles of that. And I'm going to take the coefficient right from the equation oh, that's not a 4, that's a 2. Sorry, that's a 2. You get 3 moles of CO2 for every 2 moles of Al2O3 that react. And that gets me here. Now what do I need to do? How do I convert moles of CO2 into grams of CO2? What do I need to know about the CO2? Molar mass. I need to know the molar mass of CO2. Getting this right off the periodic table. So it's 44 point, is that right? Yes. 44.01 grams of CO2 for every mole of CO2. So I'm going to put the mole of CO2 down here, because that's what I want to cross out. And I'm going to put the grams of CO2 up here. And notice, the only unit left here is the unit I want in my answer. There's an equal sign here. So everything on this side of the equation has to equal that on that side of the equation, which means the unit on this side of the equation has to match the unit on that side of the equation. That equal sign says. Those two sides of that expression are equal. And then you can pick up your calculator. And you got 12 times 3 times 44.01 divided by 2. Wow. We get a lot of carbon dioxide, don't we? $792 grams, is that right? Agree with that? We get 792 grams of carbon dioxide. Okay, number 6. All right, now 6, we're going to go, this is what we call stoichiometry. This is mass to mass calculations based on a balanced chemical equation. This is the mass relationships in a chemical equation. Now think about it. Alcoa, again, we're dealing with Alcoa right here. You can't go into the CEO's office and talk to him about moles. He's not interested in how many moles of aluminum they're going to produce that month. He doesn't sell it by the mole. The marketing people don't sell it by the mole. They sell it by weight, by grams, kilograms, metric tons. They're selling aluminum. That's what people are buying it by. If they put a price out there, $352 per mole, their customers would, their eyes would glaze over and they'd say, forget it. I'm buying my aluminum somewhere else. I don't even know what I'm paying for. But if they say, that it's $1,200 per metric ton, people understand them. They can convert that. So we are interested in mass-to-mass relationships in these chemical equations. I go over in the lab and I want to conduct a reaction. What am I going to do? I'm going to weigh my stuff out on a balance in grams. I'm going to weigh out a certain number of grams of aluminum oxide, a certain number of grams of carbon, and conduct a reaction and weigh my products in grams. So this is what we're really, really interested in here. Grams to grams relationships. So let's get a problem here. Let's see. Okay, I'm going to use this terminology here, an excess of aluminum oxide available. All right, so I want to go from grams. I want to go from grams of carbon to eventually grams of aluminum. All right? But the only relationship I know, looking at that equation, is the molar relationship. You get 4 moles of aluminum for every 3 moles of carbon. All right? That's the only thing I really know. You get 4 moles of aluminum for every 3 moles of carbon that react. Okay, now, when you see a problem like this, you'd say, well, what about how much aluminum is there? And we're just saying there's plenty. You're not going to run, not aluminum, aluminum oxide. How much, is there enough aluminum oxide to react with this 112 grams of carbon? The answer is yes. There's plenty of aluminum oxide. You can't make any aluminum if you don't have the aluminum oxide, right? So in this particular problem, we're saying we have plenty. Don't worry about how much of this is available. There's tons of it. But we only have 112 grams of carbon. So we're going to convert the grams of carbon into moles of carbon. And then we're kind of this kind of problem then. We're going to convert the moles of carbon into moles of aluminum. And then we're going to convert the moles of aluminum into grams of aluminum. That's the path we're on. So we're going to go from grams of carbon to moles of carbon to moles of aluminum to grams of aluminum. And I'm going to just set it up in a, I'm not going to even pick up my calculator until I have moved from grams of carbon to I'm ready to calculate grams of aluminum. So I have 112 grams of carbon, and the molar mass of carbon is an easy one. I got 1 mole of carbon is 12.01 grams of carbon. Now notice when I write these problems out, I don't just say 1 mole per 12.01 grams. Because I've got moles and moles here, I need to know moles of what? Moles of carbon, moles of aluminum. And so now I'm right here. Now to convert moles of carbon into moles of aluminum, I need to put my moles of carbon down here, my moles of aluminum up here. And what is that relationship? You get 4 moles of aluminum for every 3 moles of carbon. Where did I get those numbers? From the balanced chemical equation. It's the only time that I use that. It's right there. Moles of carbon cross out. So now I'm right here. I've converted into moles of aluminum. So now how do I convert moles of aluminum into grams of aluminum? Okay, you need the molar mass, which is what? 26.98 grams of aluminum for every 1 mole of aluminum. Moles of aluminum cross out. All right, you see what I've gotten to? I've walked my way over to here. Grams of aluminum. And so then pick up your calculator. Everybody do these calculations so that you see that you are getting the same number we're getting. And this is your least accurate number right here. You know the mass of this carbon to 3 significant figures. So the best way to report the mass of the aluminum is 3 significant figures. What do you got? 335 grams of aluminum. Okay. Now, let's see. Okay, that's problem number 6. I said I was going to put 4 different problems over here. I'm trying to think of a 4th one. Oh, the number 6 is kind of 2 in 1. This is, you can see that carbon here is a reactant. It's a reactant. And we're asking the question, how much aluminum could we make from 112 grams of carbon if we had plenty of aluminum oxide? This is a theoretical yield problem. All right? You're gonna hear me using this term. Theoretical yield. See the word here? Can be made. Do I always get exactly 335 grams of aluminum? As a matter of fact, you'll never get 335 grams of aluminum. If everything was perfect, the temperature was perfect, if every bit of carbon reacted you got a complete reaction, then you could get 335 grams. So that's your theoretical yield. What does Alcoa get? They always get something less. That would be your 100% yield. If they got 335 grams under these conditions, they would have 100% yield. But if you went to Alcoa and said, what is your yield usually? They'd probably say, oh, it's about 97.5% or 98.8%. We don't get why. Well, we lose some of the carbon. There's stuff on the inside of the kettle that we can't get out. The reaction doesn't go to completion. So this is your theoretical. Theoretically, what's the best you could do? This would be ideal conditions. You could get 335 grams. So that's what we're talking about there. So 6 is, typically you use this when you're talking about, I've got this much reactant, how much product could I make? That can I make? Right? And we'll talk about actual yield. Let me try, well, let's see here. I was going to pull up your homework. Do I have a problem like that? Aha. I do. Okay. This comes right off of homework number 2. Chapter 4, homework number 2. I don't know if you'll get this problem, but you might. I'm going to write it on the board. I want you to solve it. And we'll take a break. As soon as I get this written up here, you can start working on it. Take a 5-minute break. Here it is believed that the reaction responsible for the depletion of ozone in the atmosphere is this. Here's the reaction. Ozone plus nitrous oxide. So in the stratosphere where ozone is reacting with nitrous oxide to form oxygen and nitrogen dioxide. These are all gases, so they have G's after each one of these. If 97.7 grams of ozone reacts with excess nitrous oxide, how many grams of NO2 will be produced? Okay? What is the first thing you have to do before you start solving this problem? Balance the equation. So number 1, balance the equation. And then number 2, do this mass to mass calculation. That's stoichiometry. All right, work on that. Take a break. We'll come back and see what we should have there. Okay? And that could be a problem that you pull up. How to connect. Well, boy, this is kind of wild. We got oxygen and everything here. This is a little tough one to balance.
Thinking that's already balanced.
Oh, it is balanced.
Is it balanced?
It is
Okay,
balanced.
Okay,
Yeah, there's 4 oxygens on both sides. I missed that.
okay.
There are
That's okay.
4
I wanted to make
oxygens
sure
on
I
both
wasn't
sides.
missing something.
Okay, that's great. That's great. It's balanced. So the coefficients are all 1. Thank you, Rochelle. Somehow I was seeing 4 oxygens on one side and only 3 on the other. But no, that's balanced. Beautiful. Okay, now what's your strategy going to be? You're going to have grams of ozone. You're going to convert it into moles of ozone. You're going to convert that into moles of NO2. And then finally, grams of NO2, right? So when I do a problem like this, it's kind of nice to just get your molar masses right up here. 3 times 16 equals 48. What's the molar mass of NO2? NO2 molar mass? .01. All right, so there you got your molar masses right there. So we got 97.7 grams of ozone. And there's 1 mole of ozone is 48 grams. And okay, even though there's a 1-to-1 relationship here, I still throw it into this equation just so that I will never forget to do this. So I have 1 mole of ozone down here. You get 1 mole of NO2 for every 1 mole of ozone. Okay, so just make that a habit. Don't just skip over that. You say, oh, it's 1-to-1, it doesn't matter. Well, it matters from the unit point of view, and it also matters so that you never skip that. If you get in the habit of skipping that, you will skip it at the wrong time. And now you got moles of NO2 right here. This is where we're at. And now we got 46.01 grams of NO2 per mole of NO2. So 97.7 divided by 48 times 46.01. So 93.6 grams of NO2. All right? Yeah, and that's balanced. Thank you, Rochelle. I was diving into a massive problem that wasn't a problem. Let me point something out. This is a common, well, we won't see it here, but here's a common mistake some students make. They'll put this in here, but then they'll have 26.98 grams of aluminum, and they'll pull this coefficient down in here again per 4 moles of aluminum, and that's not true. What is this? This is 26.98 grams per 1 mole. That's the molar mass. That's what molar mass is. Grams per 1 mole. Only use this coefficient once. Only go into these coefficients once in this calculation. That's when you're converting the moles of one thing into the moles of something else. That's the only time you need to use those coefficients. All right, in this particular case, it doesn't matter. It's a 1, so you wouldn't even notice it. But that's a common mistake. Not real frequently, but every so often people get a little confused about that. Okay. Very good. So let's see here. Let's go back to where we were. I forget. Okay, that's probably the last slide, or this was the last slide we got to last Thursday. Is that right? Something like that. We were looking at what a mole of different things looks like. You've got slides here, and I'm not going to dwell on these. They're repeating what I did, what I went through with the aluminum oxide example, but you've got slides here to go back and look at them. If you, what happened? If you look here, here's the reaction of hydrogen gas with oxygen gas to form liquid water. So hydrogen-powered automobiles. This is the reaction. There are automobiles, tanks of hydrogen in the back. I think there might be some taxis up in Dallas that are running around Dallas like this. Why? To decrease the carbon-based pollution in high urban areas. I don't know what they're doing in Los Angeles, but they're probably trying to do this kind of thing in Los Angeles. Power some things with hydrogen. So you just take the oxygen out of the air, and what's coming out of the tailpipe of the car? Water vapor. Now it's coming out as steam, but at room temperature it cools back down and liquefies, and there it is. That's an explosive reaction. You get a lot of hydrogen together, you have to be careful. It can explode. That's an explosive reaction. So that's an automobile that's run on oxygen. And you're representing the element. So if it is nitrogen, or if it is hydrogen or oxygen, nitrogen, bromine, you're writing it as the diatomic, you're writing it in the form it exists in, going into that reaction. So, you got two H2O molecules plus 1 oxygen molecule forms 2 water molecules, or 2 moles of hydrogen plus 1 mole of oxygen forms 2 moles of water. Okay, here is a decomposition reaction. I'm sorry this is so tiny. You can kind of blow that up a little bit. How do you notice a decomposition reaction? Well, there's only one reactant. There's only one thing on the left side of this equation, mercury 2 oxide. Mercury 2 oxide, with plenty of heat, is going to produce elemental mercury and elemental oxygen. It's decomposing into its original elements. All right, and they're just showing you it here. This is mercury 2 oxide, a kind of a red powder. Plenty of heat. You'll drive the oxygen away, and you end up with liquid mercury. You got to do that in a hood. You're boiling the mercury, so you're going to get a lot of mercury vapors coming off of there too. So, but that's a decomposition reaction. I have a few slides on another set of slides here. It talks about types of chemical reactions. So I'll talk about them in a little more systematic way, but I'm just pointing out what kind of reaction that is. That's decomposition. products and reactants must be specified using their correct symbols. That's mercury 2 oxide. That's oxygen, and that is elemental mercury. Balancing. You use coefficients to balance. All right? You look at this equation. I've got 2 oxygens here. So how do I get that? I need to put a 2 here. To get my 2 oxygens, what does that do? That means I need 2 mercuries. So 2 moles of mercury oxide produces 2 moles of mercury and 1 mole of O2 gas. So a chemical equation represents a chemical change. Here are some real common ways of evidence that a chemical reaction has occurred. You take mercury oxide, there's no gas there, and you see a gas forming. You have a red powder and you end up with a silver liquid. New properties. You might have a precipitate form. You mix 2 solutions together and everything's soluble. You mix them together and you get a precipitate. That's the evidence of a chemical reaction. Heat. Now, heat isn't always proof that a chemical reaction occurred, but it's suggestive of a chemical reaction. Sometimes just dissolving things in water will produce heat. Color changes. These are some of the things. All right, some of these slides are just good ones to go back. Here's hydrochloric acid, aqueous, reacting with solid calcium, forming calcium chloride and hydrogen gas. Now they're looking here at possible ways of representing this. This is incorrect because that's not the correct form of hydrogen. Here's the correct form of hydrogen. Here's the correct formula. Let's see, that's an incorrect one too. Yeah, okay, so here is your 2 HCl's, 1 calcium, forming calcium chloride, CaCl2, and H2. So there's your correct equation, balanced correctly. What is HCl? It's this molecule, HCl. All right, we've talked about balancing. So here's some you can go back to. All right, let's take a couple examples and just try to balance a few more equations. There's about 3 or 4 examples here. different kinds of chemical reactions. All right. You could break this down into silver, nitrogen, oxygen, iron, and chloride, but just experience talking here. I look at that, and what I see over here is I see silver, I see nitrates, iron, and chlorides. And over here should be the same thing. Because the silver nitrate is ending up as a nitrate, iron nitrate, I just treat that as a unit. I can't always do that. I could give you examples where you start out with a nitrate and you get nitrogen gas and oxygen. So you can't always do this, but I take a look at this. I see nitrate on the left, I see nitrate on the right. I could just keep it that way. So I have 1 silver, I have 1 nitrate, I have 1 iron, 3 chlorides. 1 silver, 3 nitrates, 1 iron, and 1 chloride. So, let's start with the nitrates. I've got 3 nitrates here. So how many silver nitrates have to go into this reaction? How many? 3. So I'll put a 3 right here. Now I've got 3 silver nitrates. I got my 3 nitrates. Well, that gives me 3 silvers. So I need to put a 3 over here to get my 3 silvers. And notice by doing that 3 to get my 3 silvers, it also gives me 3 chlorides. And it's balanced. Okay? We could have broken it down to the nitrogens and the oxygens, but it would have just been, two elements we had to deal with, and then just use the nitrate as a package deal. Okay, go ahead and balance that one. This is nitrogen gas reacting with hydrogen gas to form ammonia. Someone have it?
Three hydrogens and 2 NH3.
Okay, so you started with the hydrogen. You saw that you had 2 on the one side and 3 on the other side, so you picked a common multiplier of 6. So what else? Oh, and it's balanced right there. 2 NH3s gives you 2 nitrogens. Balanced. Very good. All right. Okay, let me explain a little bit here. This is a category of reactions that you can see many of these. This is a hydrocarbon reacting with oxygen to form carbon dioxide and water, and you could just keep changing the hydrocarbon and nothing else changes. It's oxygen, carbon dioxide, and water. You just have to balance it differently. And for example, we could have methane. This is propane, what we have right here, H8. We could have butane, H10. We could have gasoline, all different kind of hydrocarbons, because that's what we basically do with hydrocarbons, is we burn them. They combine with oxygen, they form carbon dioxide and water. So the rest of the equation stays the same. So what we're going to do here is the choo-choo method. Choo-choo. All right? What I mean by that is balance this in this order. Get your carbons balanced, get your hydrogens balanced, and then finish off your oxygens. So if I look on the left side here, this molecule has 3 carbons in it. I'm going to do this example, and then I'm going to give you another one to do, to just follow this method. So to get my 3 carbons over here, I put a 3 in front of the CO2. Again, notice that we're not changing formulas. We've got the right formulas representing the reaction. I've got 8 hydrogens over here. Every water molecule gives me 2 hydrogens. So I'm going to need 4 water molecules. 4 H2Os would deliver 8 hydrogens. So that's how those 8 hydrogens come out of this reaction as 4 water molecules. Okay, now I'm going to come on over here now. I've got my carbon and hydrogen balanced and ask the question, how much oxygen is represented in my products? Because that's how much oxygen has to be on the reactant side. 3 times 2 is 6, plus 4 times 1, there's a 1 right here, is 4. That's 10 oxygens. So I've got 10 oxygens. A 5 right there will give me 10 oxygens. Okay? So CHO. Do the carbon, the hydrogen, and then the oxygen. Do the oxygen last. All right, now this very next one is butane. So go ahead and, all right, this one's going to give you a little bit of trouble, but use that method to do butane. So what problem do you get into? You're getting an odd number of oxygens? Yeah. Okay, so how are we going to deal with that? Okay, double everything. So right there we get 8 oxygens plus 5 oxygens is 13 oxygens, which is 6 1/2 O2s. That would be balanced, but it leaves a fraction in the final balancing of the equation, and we don't like that. We like to see whole numbers, integers. So you can multiply every coefficient times 2. This is like making pancakes. You have oil, eggs, flour, and what else? Oil, eggs, flour, and milk. You got 4 ingredients in your pancakes, and it makes 12 pancakes. You want 24 pancakes? You don't just double the eggs. You double everything in the recipe. Doubling the recipe means you double everything. So here, if we want to raise each one of these coefficients, double every coefficient, so we're going to get 2 times 1 is 2. So 2 times 1 is 2. 2 times 6 1/2 is 13. 2 times 4 is 8. And 2 times 5 is 10. So really the final balanced equation is 2 CH4s, 13 O2s, 8 CO2s, 10 H2Os. That's the final balanced equation. Any questions about that? Okay, I'm going to just leave that one to you. That one's a little bit harder. That is ethanol. That's actually the alcohol in alcoholic beverages. So if you were taking ethanol and burning it, you would get CO2 and water. And but in this case, you've got oxygen on the reactant side. You have an oxygen in your here in your reactant. So you have to take that into consideration. I'll let you deal with that one. Here's acetylene. This is the reaction in the acetylene torch. C2H2 is acetylene, and pure oxygen, you get a really, really hot flame. This is what they use to cut through steel with an acetylene torch. There's another one, that's butane. Well, we did that one. Acetylene again, okay. All right, calculations using the chemical equation. This is what we did a little bit ago. This is what this was all about. So I just want to point out there are other slides in here that can ask questions. These are problems you could go do to solidify this. I think rather than dwell on more of these problems, I'm going to try to cover all the concepts that are in chapter 4 today, so that on Monday we can cover chapter 5. So keep in mind, you got slides here. You can look them over, see what they're telling you, follow them, scratch them up, solve some of the problems. All right, what's the other? All right, I introduced the word theoretical yield, or that phrase to you. What problem are they? All right. Okay, let's do this one real quickly. Calculations using the chemical equation. Calculate the grams of sodium that will react with. No, let's not do that one. They got some numbers here. I'm not sure where they're getting these numbers. Percent yield. And we got the theoretical yield. That's the maximum amount of product that can be produced. If you run a reaction, I'll use this one as an example. If you ran a reaction, you would calculate the theoretical yield, and then you actually got your product and went and weighed it. You said, okay, this is how much I actually produced. What was my percent yield? So, okay, let's use this example right here. I'm right here. Number 6. This was our theoretical yield. If I started with 112 grams of carbon, theoretically I should be able to make 335 grams of aluminum. But let's say that we did that reaction. We started with 112 grams of carbon. We did the reaction and we found out that we had 305 grams of aluminum. This is our actual yield. We already calculated that the theoretical yield would be 335 grams. So what is our percent yield? Our percent yield is this equation. Actual divided by theoretical times 100%. That's how you calculate percent yield. So I would say, okay, I isolated 305 grams of aluminum at the end of my experiment. I could have theoretically made 335 grams of aluminum. That would have been 100% yield. So 305 divided by 335 times 100. That means I got a 91.0% yield. Okay? You see that? I got 91.0% of what theoretically I could have made. So it was 9% short. There's 9% loss. So if Alcoa is out there with an overall yield of, let's say, 98%, and they got a competitor that is producing aluminum at 99%, they actually are getting 1% more aluminum every time they run their reaction. They could have a competitive advantage. So Alcoa does try to up their yield. The higher the higher the actual yield, percent actual yield, the less waste, less stuff you're throwing away, the less raw materials that you're buying and just wasting. So you're able to do things more efficiently. Pharmaceutical companies have historically awful yields, okay? They get 5-6% yield. Why? They start out with this raw material, they make this compound, they get all these other side reactions, they have to separate out all those things because this is the compound they really want. This is the active drug, and they got all these other reactions, side reactions that are going on, and they got to purify their product, separate the real effective drug from all this other stuff, which ends up being waste, or they got to find out some other use for it. So pharmaceutical companies have horrible yields, but what they need is really pure, effective compounds. Industrial companies like steel companies, aluminum companies, they get much higher yields. Okay. All right, so that introduces you to this theoretical, actual, and percent yield concept. Okay, this is 4.95 in the text. We're starting out with, we won't do this problem, but let's just look at it. We've got 20.0 kilograms of acetylene. This is acetylene right here. And what's the question? How much CO2? How much in grams of CO2 is produced by burning 20 kilograms of acetylene? Okay, this is a little bit tricky because that's kilograms. And remember, molar masses are in grams. You're going to have a molar mass up here. So the molar mass of this is 26.04. grams per mole. Grams per mole. This is kilograms. So I think the best thing here would be to convert this into grams. So that would be the first thing you would do. There's 1,000 grams per kilogram. Because you're going to convert, you want to convert your acetylene into moles. You're going to go from this to grams, and then to moles of acetylene, to moles of CO2, to grams of CO2. So first step there would be to take your kilograms into grams. All right, and then it becomes that kind of a problem. This is the most important kind of problem for you to be able to solve, this stoichiometry. It requires these skills. Converting grams into moles and converting moles into grams. Or wait, moles into grams and grams into moles. So it requires both of those skills. It requires this skill, getting your molar mass. Okay, so this thing brings all of that together. You're given an equation, you balance it. Now on an exam, when I give you this kind of a problem, I'll give you a balanced chemical equation. So on the exam, there will be some questions that say, balance this chemical equation. So there's questions that are testing your ability to balance equations. And then here, when I'm testing your ability to use these mass calculations, I'll give you a balanced chemical equation. Because, I mean, if you can't get it balanced correctly, you can't solve the problem. You can't solve this problem with an improperly balanced equation, right? Because you've got these coefficients that are fundamental to getting the correct answer. So you have to have the right coefficients. So I will separate those two skills out in questions, or at least I'll make that attempt to do that. Sometimes a question flies in that I miss, but that's what I try to do. That's what I definitely try to do. All right, so these are some examples. I'm going through a whole bunch of slides, but they're examples of this. That's the last one. All right, I'm going to pull up another slide set, which is types of reactions. So why don't you take another short break, and I'll bring up this second set of slides, which really talk about types of chemical reactions. All right, here's types of chemical reactions. There's a couple different ways of classifying chemical reactions. We're going to just use some real the most critical ones. And what you need to do on some of these reactions is just kind of start seeing certain features that tell you what type it is. So there's two ways. There's one way of talking about simple replacement, double replacement, decomposition. I mentioned that. Another little category is acid-base reactions, oxidation-reduction reactions, precipitation reactions. Those are kinds of chemical reactions. Okay, so here's one simple category is combination reactions. An element plus another element forming a compound. Or, sometimes it can be an element with a compound forming a new compound. But combination, you have two things coming together as reactants to form a third final product. Combination reactions. So there's an example. Sodium plus chlorine forms sodium chloride. Hydrogen plus oxygen forms water. Those are combination reactions. All right, decomposition. And we looked at this example earlier. That little spot is in a very inappropriate spot. Let's move that up a little bit. Decomposition. Now, how would you recognize this? When you see a reaction that has only one reactant and it's going to produce two or more other things, it is breaking apart. It's decomposing into other things. So this was the example on the earlier slides, mercury 2 oxide forming mercury and oxygen. If you took any combination reaction and wrote it backwards, sodium chloride forming sodium and chlorine, all right? Decomposition. Took any combination reaction and just wrote it back, wrote the reverse of it. I don't say write it backwards. Write the reverse of it. Write the reverse of it, you have a decomposition reaction. How do you take a certain compound and decompose it into its other reactants? So that's decomposition. All right, so I'm showing you combination, decomposition, single and double replacement. Those are certain classifications. These are types of reactions: precipitation, combustion, acid-base, and what was the other one I said? Oxidation reduction. There you go. Oxidation reduction. These are now the hydrocarbons reacting with oxygen. That's combustion. When you're burning methane or propane or gasoline, it's combustion reaction. All right, acid base, and then oxidation reduction. All right, so in each one of these types of reactions, you have to kind of look and try to see certain hints or clues that it's this type and not that type of a reaction. All right, what's the clue? All right, let me show you the major clue that you're dealing with a precipitation reaction. This is the one place where these coefficients, there are these little tags on the end, are going to be so critical. Now, this is, imagine I got these flasks in here this morning. Here's silver nitrate in solution. AgNO3 with an AQ after it. What is that telling you? This silver nitrate is soluble in water. It's floating around in there as silver ions and nitrate ions floating around in the water. It's clear and colorless. You could see your hand through that solution. It looks like water. If I had a glass of silver nitrate sitting here and a glass of water sitting here, you wouldn't really know the difference based on appearance. It's going to look like water. Here is sodium chromate, Na2CrO4AQ. That's telling you sodium chromate is soluble in water. Now that is also clear. You could see your hand through it, but it is not colorless. You'd be pretty sure that wasn't water. And that wouldn't be very safe. Well, neither of these be safe to drink. But here's you got chromium, chromate. But they are soluble. The silver nitrate, the sodium chromate are soluble in water. That's your starting materials. Okay, now what do you do over here? You pour these two flasks together into one flask. And what happens? Now notice what you have in the two separate flasks. Sodium ions, nitrate ions, silver ions, nitrate ions, sodium ions, and chromate ions. You pour them together, and all of a sudden now, this ion sees that ion. Here, this ion is in this flask. This ion is in this flask. They meet and react and form a solid. Precipitate. This is what that S is telling you. That this is, you can't put an AQ after there because silver chromate is not soluble in water. So it precipitates out of the water and is an indicator that a chemical reaction has taken place. Silver ions have combined with that to form this insoluble product. And your sodium ions and your nitrate ions are still floating around in there. So what have you got there? Sodium nitrate aqueous. So that is your clue right there. When you see two solutions that are soluble in water mixed together and you see the formation of a solid, precipitate, then that's a precipitation reaction. That's your best clue. All right, so there's a good example of that. There are ways of predicting whether a precipitate will form. And I have another chart that I like a little bit better than this one. But this chart here is kind of telling you, yeah, Jose, you were asking the question earlier, how do I know whether something is solid, liquid, or gas? What's its physical state? Well, this chart would be the chart you use to predict whether something is going to be soluble in water or not. This is your simplest rule right here. Well, these two rules right here. Soluble. Sodium, potassium, ammonium compounds are soluble in water, and there are no exceptions. So sodium anything. Look at right up here. Sodium chromate was soluble in water. Sodium anything is soluble in water. Rule number 2, nitrates and acetates are soluble in water, no exceptions. That would have predicted that silver nitrate would be soluble in water. Why? Because all nitrates are soluble in water. Doesn't matter what it is. Sodium nitrate, magnesium nitrate, calcium nitrate, barium nitrate, silver nitrate, lead nitrate, mercury nitrate, They're all soluble in water. Chlorides, bromides, and iodides are soluble in water, except, so this has some exceptions. Lead, silver, and mercury compounds, chlorides, bromides, and iodides are not soluble in water. So silver chloride would be would precipitate. If I took silver nitrate and I reacted it with sodium chloride, this is soluble. Why? It's a nitrate. This is soluble. Why? Because all sodium compounds are soluble. I would get silver chloride. This silver is going to see that ion and form a precipitate. All right? So how do I figure out what these things should be? Well, all sodium compounds are soluble. All nitrate compounds are soluble. So this is going to be soluble. But silver chlorides are not soluble. Predicting a precipitation. Lead nitrate. All nitrates are soluble in water. Sodium chloride. All sodium and most chloride compounds are soluble in water. So if I had this plus that and I said finish this, you'd have to say, well, let's see. Lead will see this chloride ion, and right here it says chlorides are soluble except lead chlorides are not. Silver chlorides, mercury chlorides, but lead. So that predicts that is going to be a precipitate. And how are you going to indicate that it's a precipitate? You're going to put that S after it, not an AQ. Precipitation reactions are the reactions where these qualifiers here, these labels, are most useful. All right, so here you would come in here and write sodium hydroxide plus aluminum chloride. These are soluble. And then you would predict what you're going to get there. Sodium carbonate. Why is that soluble? Because it's sodium. All sodiums are soluble. Nickel bromide. Chlorides, bromides, iodides are soluble except for some things, but nickel was not one of those exceptions. So then you could, from the chart, you'd say, okay, if I had a nickel carbonate, would that form a precipitate? You're always taking a positive ion with the negative ion. You're never saying, would carbonate and bromide precipitate? No, they're both negative ions. They would never even be attracted to each other. It's always a positive with the positive with the other negative ion. The positive with the other negative ion. And aluminum hydroxide, let's see what they say about hydroxides. Okay, now on this side of the chart are things that are generally insoluble. Hydroxides are generally not soluble in water, except if they were sodium or potassium or ammonium, calcium or barium. Okay, aluminum is not one of those. It's not one of these exceptions here. So aluminum hydroxide is not soluble in water. So it's saying these hydroxides and sulfides are soluble. But aluminum hydroxide is not one of them. So I come up here and I say, so I just turned on my camera. That's a precipitate. Now the other ions, what are the other two ions there? If I got my aluminum and my hydroxide, what else? How do I finish that equation? Sodium chloride. And what do I put after it? Soluble. So I put an AQ. Yeah, that S doesn't mean soluble. That S means it's a solid. Okay? Don't get confused. That S isn't saying that is soluble. It's saying it's not soluble. It is a solid. Okay, let's look at acid-base reactions before I look at oxidation reduction. Okay, now on acid-base reactions, what you need to look for is an acid and a base. What are acids? Acids generally have an H in them. That's hydrochloric acid, nitric acid, sulfuric acid. This is acetic acid or vinegar. Acetic acid, H's. You see them leading with an H. That's your acid. This will go into water and form a hydrogen ion and a chloride ion. This is your acid. An acid is a compound generally that produces a hydrogen ion when it dissolves in water. What are bases? Bases generally have a hydroxyl group, an OH. Oh, I meant to be sodium. NaOH, KOH, barium hydroxide. These are bases. Aluminum hydroxide would be basic. Trying to think some others. Lithium hydroxide. All right, those are all bases. And what do you have? An acid plus a base, up there on my slide here, forms a salt plus water. That is the general acid-base reaction. That's what you're generally seeing with an acid and base. You can see that hydrogen and that OH forms the water molecule. Acids have low pHs, 1 to 6. Bases have higher pHs, 8 to 14. They neutralize each other. This is a neutralization or an acid-base reaction. An acid neutralizing a base. You form a salt. Now, sodium chloride, you know, is salt. But, I mean, you could have HCl reacting with KOH, and you would get a different salt and water. Instead of sodium chloride, you get potassium chloride. You could get barium chloride, barium nitrate. You just get different salts. Chemists say, what is a salt? It's the product of a reaction of an acid with a base. Forms a salt. So those are acid-base reactions. Let me just point out one thing about these precipitation and acid-base reactions. If I were to dissect one of these, let's just take the HCl plus the sodium hydroxide, forming the sodium chloride plus the water. The charges the charges on these different species would not change. This is a +1 and a -1. +1, the hydroxide is a -1. +1, the chloride's a -1. And in here, the hydrogens are +1s and the hydroxide's -1. In other words, this charge or this thing keeps its same charge. This keeps no change. No change in charge. That'd be likewise with the precipitation reactions. You'd see the same thing there. Let me see an example here. Yeah, here this is a +1, -1, +1, -1, +1, -1, +1, -1. The nitrate doesn't change its charge. Silver doesn't change its charge. All right, why am I pointing that out? Because when you go to oxidation reduction reactions, things change their charge. Charges change. So you need to know a few of the rules about charges. Elements have an oxidation number of 0. Any element in its elemental form has an oxidation number of 0. Elemental silver, 0. All right? What about if the substance is in a compound, like an ionic compound here, you can tell what the charge is. Nitrate is a -1. The nitrate ion is NO3 -1. So what does that make the silver? +1. But notice that your +1 silver as a reactant is coming out as metallic silver, elemental silver, 0 charge. That's a change in charge or change in oxidation number, which indicates that you got a redox reaction or oxidation reduction reaction. Whenever you see something going from one charge to another charge, electrons have been involved and the oxidation or reduction has occurred. Okay, reduction means lower charge. The charge has reduced, gone down. So where has the charge gone down? The +1 silver has gone down to 0. So it's gone from +1 to 0. That's reduction. The zinc went from 0 up to +2. Its charge went up from the reactant to the product, was an increase in the oxidation number. It got oxidized. That's oxidation. Okay, how are you going to remember this? Well, remember this. Oil rig. Oil rig. Oxidation is the loss of electrons. Reduction is the gain of electrons. Reduction is the gain of electrons. Okay, if you gain a negatively charged particle, it lowers your charge. Follow me that? Follow that? You're gaining something. But what is that something? It's a negatively charged particle. So it makes the charge that's on that species that gained that electron go down, be reduced. Gaining electrons is reduction. Now notice here. We got 2 silver ions, plus 1 charge, plus 2 electrons, forms 2 silver atoms. So the plus 1 went to 0. Each of these electrons is drawing down that charge on each of those silver ions to 0. That's reduction. Reduction is the gaining of electrons. Silver ions plus 2 electrons is reduction. It's gained electrons. Oxidation is the loss of electrons. So elemental zinc loses 2 electrons. It becomes the zinc plus 2 ion by losing 2 electrons. So oxidation is the loss of electrons. We always talk about oxidation reduction reactions. You will never talk about an oxidation reaction. Oxidation doesn't happen unless reduction happens at the same time. Okay? So they are always oxidation reduction reactions. Something is being oxidized, something is being reduced. Now, why is this important? You get in your car, you put the key in the car, you turn the ignition, it completes the circuit between your battery and your starter. And start, the car's not running. So what's going to run the starter? The battery. What's the battery doing? It's got a redox system. That battery is an oxidation reduction system in that battery in your car. For what reason? To generate electrons, to generate electricity, and a lot of electricity. Because it takes, you remember the old Model T4s, and the guys out there trying to start their Model T4. What are they doing? They are the starter. They're trying to turn that engine over and get it running. Well, we now have electric starters in our cars that are doing that for us, but they're running off of an oxidation reduction battery. All batteries are oxidation reduction systems, oxidation reduction reactions. And what you do is you separate the one part of the reaction in one part of the battery, the other part in the other part of the battery. So now there's, this thing wants electrons from that thing. So you make a circuit so that the electrons have to go through this electrical wire to get over to the silver, and you got an electrical current. That's how you're generating an electrical current, through a chemical oxidation reduction system. All right, these are probably the hardest ones to identify, but just know that there's your copper. It's got a 0 here. It's got a +2. I've got 2 nitrates. So boom, up to there, I got a +2 here. That's copper metal, 0. 0 is going to +2. So is this being oxidized or reduced? Oxidized is the loss of electrons, and it makes the charge go up. So that copper is losing 2 electrons to become a copper +2 ion. So that's your oxidation. This is oxidation. And the silver is being reduced. It is gaining electrons. Reduction is gain, rig. Oxidation is loss. Okay? So that's how to identify some of these. All right, let's... all right, don't worry too much about this. There are some slides like this, but I'm generally not going to expect you to complete a chemical reaction. I mean, you could say, well, how do I figure out what's going to be made there? Well, you can do these things, but don't worry. Probably the only exception might be in a situation like this, where I might say, okay, I got lead nitrate aqueous, I got sodium chloride aqueous, and I wouldn't, I wouldn't give you this part of it. think? Can you predict the precipitate? And how do you do that? You use these solubility rules. Okay, I think this is finishing off these slides. Now there's one, I mean, you remember, everything that's on this side of the equation has to show up over here. And this is a little bit simpler one to, we've got aluminum, we've got our hydroxides, it's not balanced, but what don't we have? What don't we have on the product side? Lithium chloride. And what would the formula of lithium chloride be? Here's lithium. What's its charge all the time? +1. There's chloride. What's its charge? -1. So what's the right formula? That one right there. So you don't write LiCl3 because you see 3 chlorides over here. You write the formula of lithium chloride. And it is soluble. Okay, here's the last slide. Classify these reactions. And then let's pull up the homework. The first one. What type of chemical reaction is that? Oh, they're having you classified as decomposition, combination, single replacement, or double replacement. I'd actually let's look at them as acid base, oxidation, reduction, precipitation, and let's see, was there a fourth type? Oh, combustion. Let's classify them this way. What type of reaction? The very first one. Acid base. Here's your acid. There's your base. So this is an acid base. All right, the second one. Okay, now Jose, why do you say that? Where do you see something changing its charge?
The aluminum and then also the nitrogen.
Okay, here's elemental aluminum, so you know that's 0 charge, and here it is in a compound, and here is nickel, you know that's 0, that's elemental nickel, it's not combined with anything, and this one would be, that's interesting, that's a +1 nickel, if that's written correctly. Usually nickel is a +2, but NiNO3, there's only one of these, so that would be +1. All right, this one isn't falling into those categories. It's falling into one of these. Decomposition, combination, single and double replacement. Decomposition, you'll have only one reactant. All right, so that's all I'm expecting with these reaction types is to get a feel for it. And what type is this?
Double replacement.
Okay, this is a double replacement. The barium is taking the place of the sodium, so it's becoming barium carbonate. The sodium is taking the place of the chlorine, so that's double replacement. And a precipitation. All right, so the two different ways of classifying chemical equations, you can have chemical equations that fall into both kinds. So this right here is telling you it's a precipitation reaction. We don't have an acid and a base. We have two salts that are soluble in water being mixed together, forming a precipitate and leaving sodium chloride still soluble in the water. Okay, so that's a kind of little fill. Yes.
If you have a solid on one side and then you have a solid on the other side, is it still considered a precipitation, or is it they both have to be aqueous on the left side or on one side?
Yeah, they both be aqueous on one side, and you're forming a precipitate.
Oh, okay.
So the precipitate's always coming out in the product. Okay, let's see. Has anybody done homework chapter 2? Chapter 4, second homework.
I did some of it, but it was like weird. I can ask you to do that.
Oh, is it really hard to format?
Yeah, well, first off, it's not very clear what it's asking out there. I like stuff like
I'm having trouble to get this display up there. See, sorry about this. Jose, does that have a problem number? Would you press auxiliary AUX? Get me back to this. There we go. Let's pull it up here. Yeah, is it coming up with a particular problem number or?
I didn't take a picture with the problem number.
Okay. Here, come and show it to me again.
Oh, you want me to show it to you?
Yeah. Let me see if I can find it. Jose's showing me one here that you got to do a lot of formatting. The balanced equation is solubility rules predict that it's soluble and it's insoluble. Therefore, black precipitate is iron sulfide. Okay, let's see if we can find that one. Or something like it. And that was homework 2.
Yes.
Classify the following reaction. Oh, what happened? Classify the following reaction as decomposition, combination, single replacement, or double replacement. That's question number 1. Someone want to take a guess? I see an acid over here, but I don't see water on the other side. All right, so if that was an acid-base reaction, you would see water over here. So I got an acid right here, but double replacement. Let's try that. Check my work. Correct. All right, let me just go down through and see if I can find that one.
It's probably like 5 or something like that. 4 or 5.
Okay, that. Balance the equation below, that's, oh. Okay, there's a decomposition reaction there. It's not asking you to classify it, it's asking you to balance it. Let's try 4. That's a decomposition reaction. Has anybody done chapter 2 homework? You, halfway? Okay. Okay. Whoa. Gotta stand it up here. So, let's just find a couple here to do. Let's try to find Jose's. 6. Let's do this one. Let's try to balance this one. Balance the equation below. Potassium oxide plus tetraphosphorus decaoxide forms potassium phosphate. Can I write on here? No, I can't. Now that I'm in Connect, I can't write on my screen. But we have this. Notice we've got 4 of these. So, I mean, one place to start would be right there. That gives me 4 of those. Notice whenever I do this thing, I write these in the same order on both sides of the equation. So I can compare right across. I don't just randomly list my elements. Whatever order I list them in on one side, I list them that on the other side. Now I've got 10 of those plus 1 here. 4 times 4 is 16 now I've got there. 4 times 3, 12 of those I've got. How do I handle this? I've got 2 here, I've got 12 over there. Times 2 is 12. Now look at 6 times 1 is 6. All right? So you just kind of start somewhere. You look at, I just kind of zeroed in on the phosphorus because I said, well, I've got 4 of them here and I've only got 1 phosphorus in my product. So at least, well, let's see what this, see how you format these. So that's gonna be a 6. That's gonna be a 1, and that's gonna be a 4, right? Check my work. Okay, I guess that, does that want a 1? Okay, now how do I do this? How do I try this again? Can't? Oh, am I gonna fail this course? Oh, hate it. Don't tell the department chairman. Okay, so what does that mean? They want a 1 in there? Okay, they want a 1 in there. There you go. Live and learn. Okay, I should do my own homework, shouldn't I? Yes, you should. Okay, I'm doing it. I'm doing it right now, folks. We still haven't found Jose's.
It's probably like next. Past those.
You stop me if there's something you really are dying to see. How many questions? There's 20 questions here. Balance the following equation. Oh, that's a toughie. Select. What's this mean? Oh, so you select numbers. Oh, that's beautiful. I04. You want to do this one? So all we have here is iodine and oxygen. Iodine and oxygen. It's the only 2 elements. I've got 4 and 2 is 6. 9 and 6, I've got 15 oxygens. I've got 2, and we have 2. Oh, maybe this isn't so bad. What's neat here is look at the iodine and the oxygen are sitting all by themselves, right? So I've got 6 iodines over here. So how many of these do I need? 3. We're going to need a 3 here. And we've got 15, whoa, we got 15 oxygens. Uh-oh. 15 is going to be 7.5 of these, right? And that's going to, we got a 1 here, a 1 here, a 3, and a 7.5. So what do we do about that? Double it. 2 times 1 is 2, 2 times 1 is 2, 2 times 3 is 6, and this is 15. Okay, let's see if it likes that. So we need a 2 here, a 2 here, what do we say, a 6 there, and a 15 there. Check my work.
Extra credit.
What'd you get?
2, 1, 5, 12.
2, 1, 5, and 12. 2. What was this here? Now I can't even see it. How can I go back? Can I go back?
You can go to like solution.
They do lot. What problem number was that?
It's 8.
2, 1, and 5, and 12. You're probably right, since I was wrong. What did we have there? What was it? I 4?
4. 9.
What happened there? 4 and 2 is 6. 15. So what did you have? 2?
2, 1, 5, 12.
5 times 2 is 10. 8 and 2 is 10. 2 and 9 is got it. Where did I get mixed up here? I had,
2, 1, 5, 12.
yeah, 2, 1, 5, and 12. There's your arrow. Okay, there's other questions. Well, there's only 20 questions on the homework. I can't believe it. Oh, well, I broke chapter 2 or chapter 4 into 2 sets of homework. So this second set is dealing with balancing chemical equations, and I hope it has these kinds of. I hope it has these kinds of problems. Does that the second one have that, or does the first one?
The first one didn't have it.
I hope the second one does, because this is a critical thing. I assumed it was in there. There's only 20 questions. Did you see any like that? These mass calculations?
I got to number 9 and then the rest I couldn't understand, so it's probably in those.
Okay. All right. And what's the due dates on these? I'm stuck.
The 11th for part 2.
The 11th. Today's the 6th. The 11th is Tuesday. All right. All right. We will start chapter 5. The reading's up there for the rest of the semester. We'll start chapter 5 on Tuesday, and I will get some homework and quizzes posted up there. And chapter 6. So we'll try to do chapter 5 on Tuesday, chapter 6 on Thursday, and anticipate a test possibly the next Tuesday, a week from Tuesday. All right?
4, 5, 6.
Yeah, 4, 5, and 6. All right.
Thank you.
Yep, you're welcome.